Hello and welcome to Techly Speaking, where scientists and engineers come together to chat about a common interest, share knowledge and satisfy some curiosity. I'm Laura and I'm joined by Jasmin and Emma to talk about material science, what it is and why it's useful for everyday life. We're also joined by an audience from the Engineering Development Trust's Roots to STEM programme, which I think is fantastic. So to get the conversation going, Jasmin, what is your interest in material science?
So I'm an engineer by background, a chemical engineer to be specific, but it wasn't until my first year at uni and literally my first day in Freshers Week I learned about material science, because there was two girls on my floor who were both doing it, and up until that point I'd never heard of it. But I find it really interesting because it's all about studying the different properties of materials and even developing new materials. So for me, it's quite fascinating.
Yeah, I echo your comment about not really knowing about it until you're at university. I think I made it all the way through my undergraduate, 3 years in a career, a PhD, and was into a research fellowship at the University of Manchester before I really realised that material science was something you could study. I could have studied it 10 years before that. Now I'm aware of it and I've been to conferences about it. I feel like I've learned so much and I understand much better how it improves life. Emma, would you say something similar, or have you got a different take on this?
I would say something really similar as well. I think especially at GCSE and A-level, there is no material science GCSE and there is no material science A-level. There's chemistry, biology and physics. And so I kind of thought that science was really binary in that sense. And, you had each topic of science fit into one of those three. I came to university and first I actually just met people who it was like a meeting people, what degrees are you guys doing? And they would say material science. And I was like, I didn't even know that was a degree because I'm doing physics. So I'm still in that binary. But then as I did more modules and even just learned more about the different research happening at the university, I just learned material science is actually also in physics, just as it's in chemistry and across the sciences. And so it's this really nice kind of mesh of all of the different science that you knew. And so I've done modules just in material science, even though I'm on a physics degree. And so I think I've just naturally learned more through completing my degree, but also through just knowing people and speaking to people about it and learning that it is this kind of umbrella term for all the different sciences that is involved.
I think that's great that you managed to do something about material science in a physics degree. I think they're becoming more interdisciplinary now, so even though you went to university to study one thing, you get to learn about broader stuff. I mean, I did natural sciences because I couldn't decide. And I think it's quite important that I've been able to move around quite a lot because I've had that mindset. And I think because you've seen more than just pure physics things, you've also got that ability to move around.
Yeah, definitely. It's really nice as well because it also feels like sometimes you're just studying something different, and after just doing 3 years of essential just a physics degree, it's nice to have differences in there and explore different things in that degree. Loads of different maths as well, but also biophysics and things like that. It's really nice to have a break sometimes from the heavy things.
And do the lighter stuff, which apparently is material science. So is there anything in particular that you discussed in your undergrad degree that you think is really relevant as any particular material?
Because I'm studying at the University of Manchester, there is a lot of focus at the university, I'm sure you'll know, on graphene because it won the Nobel Prize in 2010, which is really, really cool that, the university that I'm studying at has Nobel Prize laureates just walking around. I think because of that, it gets put into the spec a lot. And so we started learning about graphene in my second year, and I've just done a more advanced course in my fourth year on graphene and on different material properties. And so I think because the university has a history of that material, they want people to know about it and do labs in it, which is really cool.
Yeah, I was doing my PhD when they announced that they'd isolated it and they won the Nobel Prize, and everyone was writing grant proposals that involved it, and honestly, you got a little bit fed up of hearing about it if you weren't working with it.
We do still hear about it. Sometimes I'll just be doing my work for my week and then I'll just see graphene come up again.
Yeah, it's one of those sort of wonder materials. I guess you'll explain more about that as we go along. And Jasmin, you said you do things in sustainability, and I think you do things related to greenhouse gas emissions as well. So are there any materials related to that that you think could be relevant to this conversation?
Yeah, definitely. So, like, steel's a really important one. So, steel gets used in a lot of things. It's used to make cutlery, cars, it's used in buildings. So, it's a material that's used a lot. But in terms of global greenhouse gas emissions, steel accounts for around 8% of total greenhouse gas emissions. So, it's like one material that accounts for like quite a bit of global warming right now.
Yeah, and it's come up quite a lot in the episodes we've done with our friendly civil engineer. So we talked about building bridges, and it was really important to building skyscrapers because it suddenly became a material that could be quite easily produced in the second industrial revolution. We don't only tend to think of an industrial revolution. It turns out there have been four, is I found out when I was researching for the previous episode. So there was a chemical engineering process, I guess, that was developed, became widespread in the 1870s, which helped contribute to this sudden increase in growth, all these really tall buildings shooting up.
Yeah, it's really fascinating because, like, steel, it has, like, certain properties that makes it, like, suitable for making really tall buildings because it's strong, but it's also, for, like, its weight and size, it's quite light. And also, like, you can pretty much turn it into whatever shape you want.
Yeah, I know there are different types of steel.
Like, in general, there's 4 kinds of steel. So stainless steel is the one that most people would have probably have touched and used because it's what gets used to make knives and forks. Carbon steel is what tends to get used more in buildings. And tool steel is what they use to make, like, tool bits. It's the main reason why it's really difficult to recycle steel right now is because there's, like, different grades of steel because they have different impurities in them to make them different characteristics.
Oh.
When you recycle steel, it usually has a lower quality than if you were to make it from, like, virgin iron. So that's why recycling steel right now isn't a really big thing industrially. You have all these different kinds of steel, but you can't mix them all together.
So you would initially think that it would be quite easy because you just refer to it as steel and it's already been through that refinement process.
Yeah. Even, like, within the 4 kinds of steels, there's, like, even more, like, subtypes, depending on, like, what you put in it. The main difference between stainless steel and carbon steel is, I believe stainless steel has chromium in it.
Yes.
Because stainless steel has to be, like, oxidation resistant, so it doesn't rust and stuff. For that reason, you wouldn't mix carbon steel with stainless steel when you're recycling. You wouldn't really get either in the end. You get some kind of hybrid.
The carbon is a really important thing, isn't it? Because it helps improve the strength.
Yeah.
But then if you put too much in, it makes it more brittle. So there are tolerances.
Yeah.
It's the carbon that is the key thing to add to the iron.
Yeah.
And then you add things like chromium, silicon, other things to give it slightly different properties, like that corrosion resistance.
Yeah, so the idea is you're engineering the steel to have these, like, specific properties for different uses in industry, but then also, like you said, just like knives and forks.
You mentioned carbon steel, that's essentially iron with a little bit of carbon in there.
Yeah.
And that's like the basis. But they both come out of the ground and they're full of impurities, iron ore.
Yeah.
And carbon is usually in the form of coal.
Yeah, usually coal or, like, coke.
Yes, you take the coal out of the ground and you coke it in a process.
Yeah.
I'm not entirely sure what that does, actually. I feel like I should know this.
Yeah, I'm really intrigued to the process behind that.
It's kind of, there's like a sort of this complicated thing about what that coking coal does, isn't there? So it's sort of, does it reduce the iron? It gets rid of those impurities in this process that was developed in the 1870s. And also you burn it to heat the components up so that you can form a homogeneous steel. Is that right?
Yeah, that's roughly right. So, like, basically you need a carbon source, but you also need the heat. Melting point of iron and steel is pretty high. So, like, right now, a lot of steel is made using fossil fuels, mostly with coal just because of cost. But in some places they use natural gas. But they are looking to make different technologies or different processes that will basically kind of try to cut out the use of fossil fuels so that steel can essentially be decarbonized. The steel sector, like other sectors in the UK and the world, like, they have ambitions to be net zero by 2050.
So when you're talking about decarbonisation, that's about not releasing greenhouse gas emissions into the atmosphere. It's not about not putting carbon in the steel.
Yeah, so when we talk about decarbonising steel production, we're looking at what ways can we cut out fossil fuel use, or what alternative carbon sources can we use, or if we can basically use different processes. There's an electric version, electric alternative to, like, traditional blast furnace technology. Electric arc furnace. Kind of really need more recycled steel for that one to work. You can also use things like biomethane instead of, like, natural gas, and also, like, biomass as different sources of carbon.
So that would also put the carbon in the steel
Yeah.
to give it the right strength.
But it'll just be carbon from a different source.
Do you know how developed those technologies are? Because there's obviously those plans to open a new deep underground coal mine. It's actually near my house.
Yeah.
And it's really controversial because it's about digging up fossil fuels. But
Yeah.
it's also going into the steel, and you can't really make the steel without it.
Definitely it's the blast furnace that's the most mature. Like, the alternative technologies, they do exist, but they're just either much smaller scale or still in, like, trial stages. There's going to be, like, a really big increase in new technologies being used just because people want basically lower carb. Well, I say lower carbon, but like steel with a lower carbon footprint, essentially.
I feel like this terminology is going to get quite confusing.
Yeah, I know. It's going to get really confusing in this episode because graphene is also carbon.
Yeah. So I think we've talked around these big engineering processes, and I guess the process of making steel, it's a chemical engineering process, right?
Kind of.
We said we were sort of interested in talking about materials, and
Yeah.
I guess most people think of material as like fabric. My PhD was in simulating atoms and how they interact with other atoms. And that, to me, is what material science is about. It's about how the atoms bond together to give a solid thing particular properties, like how strong is it, how bendy is it. So I see you both nodding, so I'm going to assume that you agree with my definition of material science.
Yeah, I agree. I mean, I don't work in material science, but like that sounds about right to me.
Yeah, I feel
No,
like
I
that's
think-
my view on it as well, with like, especially with how like the structure gives you different properties. That's what I would class as material science from like a physicist, so maybe I've got it all wrong.
So material scientists will throw around terms like grain size and crystal lattice. It's kind of odd to think about the fact that steel is crystals.
Yeah.
It's little tiny crystals that have all sort of formed together. You tend to think of crystals as being shiny things like diamond, another form of carbon.
I always think of steel on a very kind of macroscopic scale. Like, I can touch steel, and I've seen it. I always imagine, like, huge, like, steel, like, infrastructures. But the only, like, material science I've really done has been very microscopic and, like, on the small scale. I mentioned graphene before. One of the really cool things about graphene is that it's a 2D material. It's not even three-dimensional. You can have layers of graphene that builds up into graphite. Imagine a pencil is made of graphite. When you're like moving your pencil across the paper, the individual layers actually like slide off because the bonding between them's weak, and that's how you get the transfer of the pencil. And then that 2D material is graphene. It's just this one layer structure. I think it's really like important to compare with probably what you guys already know, which is diamonds. Diamond is made entirely of carbon, and because of the electrons that are around the carbon atom, when they bond with 4 other carbon atoms, you get this strong 3D structure, which is your diamond. And in graphene, those carbons only bond with 3 other carbons, and so you have this spare carbon that's unbonded, and this leads to really cool properties in graphene. One, that it's 2-dimensional. Another one is that you can form weak bonds between these layers, and then you get graphite. But also this free unbonded carbon gives it some electronic properties because diamonds don't conduct, but graphene does. The bonds that they form are very, very, very strong. So I was actually looking into it and found a stat. Graphene is 100 times stronger than steel. What steel, though, did not say. But I thought that was interesting because it's the classic analogy of ants being one of the strongest creatures because they can carry so much more times their body weight, but ants themselves are not strong. And so I think that's the case of graphene. It's very, very strong, but you can't make a macroscopic thing out of a 2D material. So a lot of people use graphene in composite materials and like putting graphene into different things to make it lighter, make it stronger, use its electronic properties. I think that's really interesting in how you bring this macroscopic thing that I can only imagine into actual real life products, such as like tires or phone screens. Apparently they have really nice optical properties that means that phone screens can be more sensitive and clear.
When you said that there's a carbon atom that isn't bonded to something, with my background in simulating atoms, I would say, well, surely it wants to be bonded to something, because that would be a lower energy state, I guess is the proper term. it'd be more thermodynamically favourable. Let's throw another random term in there. So essentially, it wants to be bonded to 4 things and it's not. What's stopping it?
I don't want to go too technical, but it's because of the energy levels that you have, they can, there's a word called hybridize, so form into different numbers, and it's just the most favourable sometimes is to hybridize into 3, and so you can form into those 3, and they're the lower energy levels. But sometimes it's more favourable to hybridize into 4, and then they become the lower ones.
Okay, so then to go from 3 to 4, you'd have to give it a bit more energy to get it into that different formation.
I think so, but I also am not even sure if you could change it from 3 to 4, because I think if you gave it more energy, like the unbonded one likes to bond with other unbonded ones, and that's like in the electrostatic force, but it's not the covalent sharing of electrons. So I don't know if it's like a tendency of different carbon atoms to rather form these 3 or rather form these 4 that like makes those happen. But I think it's something like that.
Graphene's a weird material.
It seems to be able to do so many things, though. Like, Emma mentioned putting it in, I think you said car tyres, didn't you? I'm pretty sure that there's a shoe manufacturer that makes trainers with it in the soles as well, and I always assume that is to give it really good grip, but also really good strength, because normally it's a compromise. So I do a lot of running, so I've got, like, road trainers and fell running shoes and all sorts. Different types of shoes for different types of running. And that's to do with the different compounds in the rubber to an extent. So I assume this graphene trainer can do all of these things. So I don't need 5 different sets of trainers.
I think I also saw it's been used in like tennis rackets and things, but I imagine because it's so light and strong, it's kind of like for durability, but also I guess the lighter a tennis racket is, the faster you can move it, so the better the tennis racket acts. But I think durability might be one of the reasons why it starts to like pop in everywhere, because if you're like, if I just throw some graphene in, see what happens, test the properties of the shoe, and you might get a better, more durable shoe with like a lighter weight. And I also saw that it can like make fuel last longer in certain aircraft. There was a term that got through about that graphene's like a green material, and I don't know if it's just in the production of it or the fact that it allows like if it makes something more durable, like trainers, you're going to purchase trainers less often, and so it makes it more green in that sense, because you're having like things that last longer and you can use things more, and if your fuel lasts longer then you need less to go to the same distance, and so it's more green in that sense. So I'm not sure if it's like a knock-on effect or if it's actually just better for the environment to produce.
No, it's definitely a knock-on effect. Right now, graphene's not really being mass-produced. At least I couldn't find evidence. Because it's a 2D material, it's actually really difficult to manufacture. The 2 main ways of producing graphene are the sticky tape method, which is also known as mechanical exfoliation, where basically you get some sticky tape, you stick it on some graphite, you remove the sticky tape, you've got multiple layers of graphene, but then you use more sticky tape to basically separate out the layers. And basically the thinner you want it, or the fewer layers you want, like the more sticky tape you need. But like, that's not a very effective method. So the other method is basically plasma-enhanced chemical vapor deposition. I'm not sure the best way to describe plasma.
An ionized gas.
And basically you just like have layers of graphene deposited on a substrate of copper or nickel, and that allows you to make really big sheets of graphene. Because plasma is an ionized gas, it's really energy intensive to make. So it's definitely just a knock-on effect because it makes stuff more durable. But maybe in the future. So it's like been 13-ish, going on 13 years since we've figured out how to create it, I guess. So there's still lots of room for like improvements, because we've had steel for technically thousands of years and mass producing it for hundreds of years.
Steel, less than 1% of the mass is usually what has carbon in it. So it's not a lot of carbon that you're putting into that iron to give it favourable properties.
No.
So I wonder if it's similar with the grippy rubber that Emma talked about and any other usage. You don't really need a lot of graphene in there to make a big difference.
I feel like it is probably the case that even just the slight differences in the compositions make a huge difference in your final properties.
That's kind of the same for steel. So you've got composition plays a part, and then you've also got how you heat it up and how you cool it down. So you'll get different shapes of crystals forming and different sizes of crystals. That's what a grain is. It's a crystal, depending on what you put in there and how you treated it.
That is not what I thought material science was. I just think bonds, and then I just don't think about anything else. Like the production process, completely new to me.
Yeah, it's part of it, I guess. How do you know what you want to make? Like a chicken egg sort of thing. I want to make this thing, how am I going to make it? Or what are the final bonds that I need to have?
Yeah.
And I mean, a lot of material science is looking at crystals, you tend to put X-rays through them to create a diffraction pattern. That pattern tells you something about how the atoms are arranged. But, I mean, you also mentioned electronic properties, and that's really important for things like solar panels. Can you explain more about the electronics side of it?
Yeah, I found a stat that it was 60% more conductive than copper. And obviously copper's like the choice to use in wires and different electronic circuits. The electronic properties comes from this carbon that's not bonded, so you have this free electron. It's free to move about, and a charge moving is current, and so you get these kind of cool electronic properties that arise from this free electron. This is really important in computer-like components. Anything you need to run on a computer, you need like a lot of transistors, and the more that you can fit onto this chip, the faster things are, the more memory it can store. It's kind of this like amazing circuit component that just can do all of these incredible things, apparently. And when you use graphene to make these computer chips, you can make these transistors smaller so you can fit more on. Everybody wants things to be smaller and more efficient. Actually, one of my lecturers today was talking about how his first laptop, when he bought it, was £1,000 then, and it had 1 kilobyte of memory. And he was like, that was insane. That was an insane amount of memory. And now I think, I don't know, even just like a photo on your phone must be something similar to that. The advancing of that is because of transistors and the, like, different circuit components getting more efficient.
Yeah, and that technique that Jasmin mentioned that can be used to make graphene, that vapour deposition method, I think that is how a lot of electronic components are used. Some components have got like a layer of silicon or something, and then a layer of something else on top, and it's all just like individual layers of atoms built up.
Yeah, I think it's what you use when you need like really thin but precise layers.
Yeah, and then you get down this whole material science thing of how good is that crystal lattice that you've just made from building up all those layers? Are there any atoms that are out of place, and what effect does that have? Do you get like electrical current leaking out of your device because those atoms aren't aligned properly?
I think in some cases, though, when things aren't aligned properly, better properties. It's called doping in semiconductors. Isn't that just like moving things about and then it changes the properties to be better for certain things?
Yes, that's how they make solar panels, isn't it? They start off with really pure silicon, and then they dope some of it with one particular atom or ion, and they dope some of it with another ion, and that makes electrons flow from one of those doped things to another of those doped things. That was not a great explanation. We did do an episode on this a while ago as well, so there's a better explanation in there. And there seems to be a real drive to create, as you said, more efficient electronics and like more efficient solar panels, certainly. And that's all about what atoms you put in there.
I think a lot of energy and effort for the research has been how can we use this material to advance this area and then this material to advance another area. For example, like steel is an old material, but it doesn't mean that it's worse than graphene because it's old and it's always been used. It just has different uses.
I get to interview people as part of my job about their research, and I've spoken to so many material scientists doing so many interesting things. And an awful lot of them say that it involves all these different disciplines, like, you know, physicists. I interviewed someone recently who's developed a material that can be used in robots, and it heals itself, and it knows when it's been damaged as well. The robot can modify its movements accordingly because it's sensed this signal of damage, and it can allow itself time to heal, and then it can carry on. And that's another aspect of material science. I should say that involves a polymer, which isn't a crystal.
No, it's not.
Some chemistry goes on there for it to heal. It astounds me how many of them say that it was this multidisciplinary team of all these people. There was a material, they were talking about spin states. I think it was about computer processors and computer memory. Someone in their team had essentially set up the experiment wrong. And when they looked into it, it turned out they'd discovered something that no one thought was really possible. And it was a more efficient way of making computer memory work based on this crystal they were using.
Yeah, there's a lot of cool things about crystals and spin states and the way they like orient themselves in the crystal can change things. It always reminds me of how like magnets work and how you just get alignment of things in a certain direction and then immediately it just becomes magnetic. And then you take away, this is like an electromagnet, you take away like a source of electric field that's aligning these different magnetic moments, they're called. But imagine like a loads of arrows pointing in different directions and then you apply an electric field and then all of a sudden they just all point in the same direction and then your material becomes magnetic.
I tried looking up for my report, like how could I describe spin state, and I decided not to. Because it seems like this really sort of abstract property of, it's about electrons, isn't it?
Yeah. There's I've learned about three main spin state models of lattices. And I'm like, are any of them even right? Because they're all like getting more complex, but I feel like even I don't know the full picture of what the spin state even is. It's just always like this approximation, and then this slightly different approximation, and then this slightly different approximation that's very hard and no one ever uses, so you just only ever use the simple one. And so I feel like nobody really even knows what the actual structure is like, because it's just all these approximations. Which is physics. If anyone wants to do physics for you, that's what it is. It's approximations.
It's not really understanding the world, but it's getting close.
Everything is an oscillator. Everything's a bond. It's an oscillator. Everything's an oscillator. Everything's a spring, actually, I should say.
Yeah, that is pretty much what I learned from when I was doing my atomistic modelling. Sounds odd, doesn't it? Thinking about atoms connected by springs.
Yeah. If you want to go into physics, pay close attention to the springs. They don't go away.
I like how we started off talking about, we're going to talk about material science. We're going to start off with the second industrial revolution, and now we're talking about weird things to do with physics. For me, material science is really important because you can see how these things affect your everyday life if you really think about it. So thinking about, the transistors that Emma's mentioned, that makes smartphones possible. Now, I remember carrying around a smartphone. It was about the size of a brick. It wasn't even a smartphone. You could call people on it, and that was it. And now you've got the internet in your hand because of material science.
Who knows what we'll have in a few more years.
That is a good point to leave on. So if you've enjoyed listening to this episode, you can find us on Twitter, and we would absolutely love it if you would say hi to us there. Thanks for listening, and we'll see you next time.
The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.